and this is the introduction. In this lab, we investigated friction between two surfaces and learned how to experimentally determine both the coefficient of static friction and the coefficient of kinetic friction. Friction is a force that opposes motion, and it depends on the type of materials that are in contact. When an object is at rest and we are trying to start motion, the friction force is called static friction, and its coefficient is usually larger than the coefficient of kinetic friction, which is friction acting on an object that is already in motion. By measuring the angle at which an object begins to slide, or by measuring the acceleration of an object sliding down an incline, we can use Newton's law to solve for the coefficient of friction between the two surfaces using trigonometric relationships. In this experiment, we collected real data, averaged multiple trials to improve accuracy, and calculated the coefficients of friction to compare theory to actual experimental values. An example of these concepts is driving a car. When the road is dry, the tires have a higher coefficient of static friction with the as flat, so the car accelerates and brakes very well. But when the pavement is wet or icy, the coefficient of friction decreases, so the tires lose grip and the car can slide more easily.
Hello, my name is Conrad and I'll be doing the materials for this lab. First off, we have the wooden block with the Velcro on the bottom. We have the Pasco track with the meter stick on it, right here. We have the Pasco wireless smart card right here. We have the angle measuring device, which is the protractor, in which we don't actually have one over here, but
We don't. We can do it with trigonometry.
yeah.
We just measure the height.
So we'll be doing via trigonometry. And we have the masses, which the professor has provided to us. We have the scale to measure the weights, which is over here. And we also have the computer with the capstone software and the data collection for the lab. Thank you. One, go.
Hi, this is Kason Kelly, and I'll be doing the procedure for Lab 9. So step 1, we measured and recorded the mass of the black and any of the extra masses provided by the lab. Step 2, we recorded the smart card and the computer with capstone software and averaged the three. Step 3, we measured the static friction coefficient by formula increasing the angle of the action track 10 degrees upward until the block is just about to start sliding.
Horizontal incline. Don't do it horizontal. If you are
We're doing it.
so this is your height.
Step 4. Next, we measured the kinetic friction coefficient by setting the Pasco track just high enough so that the block would start sliding down. We used the wireless smart card to measure the acceleration of the block down the incline. We recorded the angle and the acceleration twice more to get an average acceleration. We computed the coefficient of kinetic friction through the formula. Coefficient of kinetic friction equals negative acceleration plus gravity times sine of theta, all divided by gravity times cosine of theta. Step 5, we recorded our data in the data table provided by the lab, screenshotted all the graphs used for the angle acceleration measurement, and we will be including it in our report. We will also answer the discussion and reflection questions in the conclusion. Thank you.
Hi guys, my name is Santiago Arras and I'll go ahead and do our data lab analysis for lab number 9. So as you can see here, we had a couple options of what we could have done our trials with. We could have done an incline, we could have done a flat. We went ahead and we did an incline kind of ramp. And so starting from there, when we lifted up the ramp, we waited until the brick itself started sliding down. We got the height, we got the length, excuse me. And so we can get our angle, and our angle for our kinetic was 28 or well, we got a height of 28 centimeters, and then before it started sliding, as you can see here, we got a height of 27, so very similar. And so using the equation right here, we got the angle of 19.75, and then right before it slides, we got the angle at 19.1 right there. So we went ahead, we did that, and should I do the graph bit too?
Yeah.
Okay. So I'll do the first one. It's right here. So we went ahead, we slapped the cart on the side because we didn't know how else to record it. But going from there, you can see that this is our static right here. So right before it slides, it swoops up. And so we just took 2 points from the swoop to get our average acceleration right there of 0.174. And then we also got our force right here. And then using that, we plugged it into this formula down here. This one right there. And so as you can see, we plugged it in for kinetic using negative 0.174. And we got 3.34 for kinetic. And our static was very close. We did the same thing and we got 3.35. So obviously our static's a little higher than our kinetic, but that's what we got. And that's the first half of this data analysis.
Hello, my name is Jorge Valdez, and this is the second part of our data analysis. So we continued our lab by doing our second and third trial. So we pretty much we're doing the same thing as we did in our first one. We got our new by doing our formula right here, and then we had to do our get our thetas again by doing the same thing as we did in the first one. And then going from there, we did our second graph, which was right here. And it's pretty much the same thing as our first one. We got our this one was our kinetic right here, and then our static was this one. So we did the calculations, and then for our kinetic we got 3.15, and our static we got 3.22, which is correct. Your kinetic is supposed to be a little lower than your static. So that's what we got for our trial 2, with our static being 3.22 and then our kinetic being 3.15. And then continuing from that, we went on to do our third trial, and it was the same setup, same everything. And then our graph for that one was this one right here. And we got we got our theta, and then we did our calculations for that one with our kinetic coming out. Sorry, our kinetic our acceleration coming out to be negative 0.187, and then for our static is negative 0.152, which were shown right here on the graph, with our mean being 0.187, and then our static, where did I say that? This one, 0.152. And then we did our calculations. We got kinetic and our static, and then for our static we got 3.24, and then our kinetic we got 3.32, which was a little weird because our static is supposed to be a little bit higher, but that's what we got. And then we averaged those out by taking our 3 for static, adding them up, and then dividing by 3. And then for our average we got 3.27, and then we did the exact same thing for kinetic. We added them up, divided them by the amount of trials, and we ended up getting 3.27 for that one. So our average for our static and our kinetic came out to be 3.27. And yeah, that's it for our data analysis.
Hi, my name is Gregorio Olivas and I will be going over the conclusion. So in this experiment, we investigated how friction affects motion and calculated both the static and kinetic coefficients of friction between two surfaces. Our results confirm that friction is a force that always opposes motion, preventing objects from moving as predicted by theoretical calculations. As expected, the coefficient of static friction was greater than the kinetic friction, showing that it takes more force to start motion than to keep an object in motion. Possible sources of error include the inconsistent surface textures, the small vibrations observed in the experimental setup, and inaccuracies in measuring forces without the sensors. Additionally, dirt, wear, or slight misalignment between the contact surfaces may have altered the coefficient values. Timing errors or sensor calibrations issues may have also affected our data. Now, overall, our findings support the theoretical that friction depends on the nature of the materials in contact and that it is an essential factor in accurately predicting real-world motion. Through this lab, we learned the importance of minimizing experimental error and understanding how friction influences mechanical systems. Thank you. Hi, my name is Gregorio Olivas and I will be going over the credits. So Steph did the introduction, Kaysen did the procedure, Conrad did the materials, Jorge and Santiago did the data analysis, and I did the conclusion, the credits, and all of the editing. Thank you.